Hello and welcome to this edition of Dr. K's Psychobabble. It's been a while. I'm used to saying the other titles of my channels, but welcome to today. We're going to be talking about audition, or how we hear, and this is a very important part of my own life personally because I actually wear hearing aids, and I'm going to explain where my hearing loss exists. Why I have that hearing loss, and why specifically it is a problem for me. But in doing so, we're going to look at the anatomy of the ear, then we're going to look at the cochlea, and then we're going to look at the basilar membrane, which is inside of the cochlea, and how that connects to the auditory cortex, which is in our temporal lobes. So let's take a look here at some anatomy. So here we have a basically cross section of the ear. We have the outer cartilage part of the bone and into the skin that makes up the pinna, the visible part of the ear, and vibrations from the air travel down the ear canal and of course impact our eardrum or the tympanic membrane. Various muscles, the various bones then vibrate against the what we call the oval window, which is on the outside of the cochlea, and that's sort of the focus of what we're going to be looking at right now. This cochlea, this little curled area of the anatomy of the ear, is kind of where all the action happens, because inside of the cochlea is what we call the basilar membrane. So this is a membrane that is made up of nerve cells that are specifically geared toward reacting and thus potentiating into a nervous signal vibrations of a particular frequency. Now this is a fluid-filled area, and fluid filling is very important because sound waves travel better through fluids. So we have air waves vibrating to the tympanic membrane. The bones out on the other side of the tympanic membrane are located in an area that is full of air. That's an air pocket there that is connected to the eustachian tube going down into our throat, that allows for equalization, and I'm going to get into the importance of that in just a little bit. But the vibrations are now, they've moved from air molecules vibrating to bones, like say solid material vibrating, and then against that oval window, and then now fluid is vibrating. And fluid is a very, very good translator of sound. In fact, the makeup of that fluid is very close to the chemical makeup of the ocean water. So this membrane is sensitive to frequencies that go from very, very high frequencies at the base of the cochlea, right at the beginning where that oval window is, all the way inside to kind of like the floppy apex, which is where all the bass notes are. So from high frequencies all the way down to very, very low frequencies. And you can map this out. You can map out these tones and sounds. So I'm going to use a little bit of an example here to demonstrate where some of these sounds exist by using a guitar. So I've mapped out the basic frequencies of regularly tuned acoustic guitar. And you'll see that the low E vibrates right around 82 hertz, and then we have the A at 110, and so on as we make our way up, with the highest note on a standard tuning guitar vibrating at about 1,174 hertz. So why not, let me get my camera ready here for a little demonstration. So I have my guitar here, I'm getting it ready for you. So here we are, here I have my acoustic guitar, and I'm going to play some of these notes, and you can imagine what they might, that they're actually stimulating the basal membrane further and further inside of that curl. Okay? Now, the first one, 82, here's bass note E. I just tuned it, so hopefully it's pretty close to an E. If any of you have perfect pitch, you're just going, that's not E right now. But this is E, right around 82 hertz. And look where that is in terms of that's right, see here's 200. You're somewhere down here is where you're looking at that. So, you know, pretty deep into the cochlea. And then the next note I have here is the A on the same string, A at 110, and then an octave from that is 220. So 110 times 2 to 220, so A 220. Those are the same note, A, but they're an octave apart, so therefore the frequency is twice as much. So you go from 110 hertz to 220 hertz. Then let's do that again to 440. So we have, you can tell my guitar's a little out of tune on that, so let's fix that a little bit here. Oh, isn't this embarrassing? And right there, we'll keep it there. So there's A220, A440, and A440 is sort of a standard tuning fork. Sometimes you get a tuning fork and it's an A tuning fork, it'll vibrate at 440. So 220 hertz, 440 hertz. And when we look at our graph, we're still somewhere here. We're still really deep in the cochlea. So a lot of what we're hearing is way down there. And then when we go one more up to 880 and we do the A right there, that note, look at that. That's an Eddie Van Halen note. We have that is 880, and we finally surpassed that 600. We're right around here. So we're looking at the guitar notes are right around here in this area. So all those guitar sounds that you're hearing are still, relatively speaking, pretty deep in the cochlea. Now, at this point, I want to explain my own hearing loss. And my hearing loss, me and my audiologist kind of go around about what it is that has caused my hearing loss, because not only did I have an incident that occurred to me that may have impacted it, but I've also had a lifestyle that has impacted it, and I have a degenerative sort of thing going on, so it becomes worse. And so there's a combination of factors that have occurred, and I want to tell you about each one of them. The first one, maybe the most elegant story of my hearing loss, was a scuba diving accident. And when I was a young lad living in the island of Guam, I took scuba diving lessons, and there was one incident where we were at about 110 feet, or we were on our way to 110 feet. Now, when you're a scuba diver, as you go down into the water is heavier than air, and the weight above you of that water produces pressure on the outside of your body. And you can imagine from the image that we had on the ear that there is pressure on the outside, and it's pushing those eardrums in. Now, scuba divers are trained to block their nose and gently push air into their mouth cavity and nasal cavity, up the eustachian tubes and into that space where all the bones are that connect the tympanic membrane to the oval window. And it equalizes that pressure. So as the outside pressure increases, we blow air into that little space, and it equalizes and we no longer feel pain. Now, as it turns out, there's one time I was going down and I was preoccupied because I was being silly. Not a good thing to do when you're 90 feet down in the water. And So I went to clear and I had a difficult time clearing, and so I forced a little bit, and I remember it like it went through, but it snapped. And we think that that might have been the beginning of some damage that occurred in the area of my basilar membrane close to the oval window, because I actually felt pain. I felt the pain of the bones being vibrated like that. And so I experienced that. I then, of course, had headphones, began playing music, began playing loud music, playing in a band for over 30 years now, and that has certainly had an effect on my hearing as well, because by and large, because I was having a hard time hearing, I never really used ear protection, and it wasn't even the thing back then. So here's what happened. What happened is there was some damage to the ability for my basilar membrane to pick up on certain frequencies, but not all frequencies. And that's why for many, many years I could not use hearing aids, because hearing aids were kind of like a blunt instrument. It's going to amplify everything. And I hear most things perfectly fine, as we will see. I'm a musician, and I play bass. Guess where the bass notes are? They're way deep inside of that floppy end of the basilar membrane. That's where most of the bass sounds. And so hearing bass sounds is very, very easy for me. Hearing the whole guitar was way down deep inside of that. So I can hear guitar things very well. What I have difficulty with is speech, and I'm going to show you why. So here we have again our basilar membrane. And let's talk about the sounds that make up speech. So the first set of sounds, let me get out of this here. Sorry, went backwards a little bit. The first set of sounds, of course, voiced vowels, the A, I, O, U sounds, very rounded, open sounds. You can imagine there's a lot of bass tonality in those kinds of sounds, and those exist in the 250 to 2000 hertz, and we look at our little graphic here and we see anywhere from 250 way in here all the way around to 2000 hertz. So we're deep in the cochlea. My damage is up here, because that's where the bones vibrated at the oval window. So this is all set. I can hear vowels, no problem. Now the next set are voiced consonants. These are B's, D's, M's, N's, those kinds of sounds right there. Range anywhere from 250 to 4,000. You should probably imagine that M, that sound has a lot of bass to it, whereas B has that initial higher frequency sound of the initial B and then the E after it, B. And so you see where it goes from 250 all the way to 4,000. Again, we're getting close. There's possibly some damage here. I don't hear those as well, but here it goes. Unvoiced consonants, F's, S, T's, those go from 2,000 to 8,000, and that goes into the area that has been damaged by my incidents. I have trouble understanding how people speak, because when we look at the way language is structured, we look at those F's, T's, S's, and one sometimes really define the word and the context in which that is happening. It also defines the beginning and end of sentences, the beginning and end of thoughts, and whatnot. So I can hear the vowel sounds. So if somebody says first, like number one, first, even as I say that, I know I don't hear it the same way you do. But I hear the IRS pretty well, ers. But the first, the F and the T on the end, particularly in the context that I was in first place, for me, I hear erst place, ers. That's right, I miss the F and I miss the T. Now, with the miraculous advances of technology, what my hearing aids actually do, and the reason I wasn't able to get hearing aids in the beginning because the technology did not occur, is it takes the frequencies that would usually be here. These are areas that I cannot hear at all. This is completely gone. There's no amplification that can bring those back to those nerves. But what it actually does is the hearing aids will retune those and place them at a different frequency. It's a different sound. Now, my brain adapts, and part of the process of getting hearing aids and using them is that the brain learns to identify an F and a T, very different experiences than you. But then after a while, my brain says, that's the new F, the new T, it's a new normal, right? And so my brain starts to process that a little bit better so that I can understand language a little bit better. End result, end game in this whole thing is I hear music just fine. I play music. I hear the guitars when they're not hidden in amplification, kind of thing like that. I can hear the lyrics. I just don't understand what they're saying. And so that is the loss. The loss is specifically that. Particularly if I'm in a crowded room where there's lots of interfering frequencies, it's very hard for me to understand what people are saying. I can hear the band without a problem. I can hear someone pounding on the table. I can hear the knock on the door. But those S's and T's are what I'm missing. Now, I didn't want to just talk about my own hearing here. I wanted to point out this sort of like really, really cool structure within our brain and within our cochlea. So we have the basilar membrane, which is basically mapped out frequencies that exist within the normal hearing range of human beings. Now, that mapping out is mapped out on the temporal cortex in the brain. So here we have an image of the temporal cortex where we process this information. And the interesting thing is we can actually, that pink area with all the different divisions, we can see where the notes are. We can see actually how the mapping of the notes along the cochlea matches the mapping of the processing areas in the auditory processing lobe of the brain, or the temporal lobe. So we can see toward the front of our heads, we see the lower notes, whatever those are, get processed all the way to the back where the higher notes are, just beyond the ability for us to comprehend those sounds or to experience those sounds. And in addition to that, we also have parts of the brain that are also oriented toward sounds don't always come in as notes, not like, it comes in as the sound of an instrument. Say, there's a multiplicity of frequencies that are happening there. So all of those frequencies are being processed across the entire auditory cortex. And then that goes into other areas processing in the frontal cortex that say that particular set of frequencies and overtones is what makes a guitar sound like a guitar, what makes an oboe sound like an oboe, what makes a trumpet sound like a trumpet, and what makes my voice sound the way it does. So I think this stuff is just amazing that we would have this mapped out frequencies inside of the basilar membrane and that it's reflected in the brain. And I need you to understand that in the development of these, the cochlea is developing and it is not connected to the brain. The brain is developing and it's not connected to the cochlea. It's not connected to the basilar membrane. Then they grow together. The same thing happens in the visual cortex. They grow together and they meet halfway. Not a very long distance to go, from your ear over to your temporal cortex. But nonetheless, the brain is ready, the basilar membrane is ready, and they meet like the transcontinental railroad. And when they meet, both structures are activated, and we're starting to be able to recognize sound. It's a damn miracle. It's very, very cool. All right, so that's it for today. That's a little bit of Psychobabble for you to digest, and I will see you next time.